There we go. Okay, let's start. Go ahead, George.
Okay, so as you know, so my project is called the modeling distributed seismicity using innovative approaches. So just a quick recap on the way of modeling distributed seismicity. So area source modeling is a type of model that we use in hazard assessment to model the hazard at a site, for example. So in the left you have an area sources. So this is Italy, and we have a lot of area sources in that case. So this is the European seismic hazard model of 2020. And in this model, they set some areas like this one. And in all these areas, well, in these areas, for example, the occurrence rate, so the magnitude frequency distribution is the same across all the area. And the parameter, for example, of the nodal planes. So when we will model the rupture into that area, they are all the same. Okay. So, and this is also the same for this area. So that it would, so in this one, we will have the same magnitude frequency distribution, same nodal planes, parameter, etc. So using OpenQuake, I generate all the rupture that the model can do, and as you can see, in that case, so this is a little zoom on that area, and as you can see, all the rupture are for the distribution of the rupture are totally homogeneous into the space. What does it mean? It means that if in that case I model also the highest magnitude into that area, and maybe the highest magnitude here is greater than 7. So it means that we have a magnitude 7 uh, that will be modeled in all the area. And this is what you get when you plot all the rupture. So the question that you may ask is, it is really realistic to have a possibility of having a magnitude greater than 7 totally homogeneous into the space? And we believe that this is not the case, and we want to change that. So the question that we want to answer is, since major fault constrain the parameter of near field fault, can a cluster of seismicity below a certain threshold can be a possible indicator of the occurrence of larger magnitudes? The second question that we may ask, and we want to maybe to resolve, is how often a large magnitude occurs without having in the surrounding seismicity of lower magnitude. And of course, if we can demonstrate this concept, the model can be used in a prospective sense to generate stochastic patterns. So it means that, okay, I will show you just after. So in order to take into account the dependence between two magnitudes, so in my case, I want to see if magnitude less than 4.5, for example, are a good way to forecast the new magnitude of 7.5, for example. So there is a paper from Foxal in that case. So what I wanted to see is if there is some ore deposits, if they are close to geological faults, or if they are not. So they developed a function called the J function, which will show the dependence between the deposit ores and the near and the geological fault. So the J function is in the bottom, and it will show if the deposits are close to fault or not. And in that case, okay, I will explain maybe a bit later. Okay, I will explain here. So let's take into account three different patterns of points. So let's say that each point repel each other. Another case will be a pattern of point that is totally homogeneous in space. And the other one will be that the points are clustered. So when we apply the J function, so it will compute, it will see if the pattern are more clustered or not. And using this function, it will show that in that case, if they repel each other, it will be the curves will be higher than uh, than a certain value. If it is exactly the same as the dashed line, it will set that the pattern is more Poissonian in space. And if in that case, if the points are clustered together, the curves will be lower than the dash one, than the dash curve. So you see that in function of the type of pattern that you have, using like the G function will permit to characterize if your pattern are more clustered or not. So the J function is made of several functions, but I will not explain here. So okay, so here I just put a simple case. So I generated two pattern of points that are totally Poissonian, so totally random into that area. So my first data set is the red circle, and the second data set is the red circle. So the black and the red. Okay, and I try to compute the J function. So the dependence between black and red one and the red circle. And as you can see in the beginning of the J function, so this is the radius here. So when we increase the radius, you will see that the pattern tend to be Poissonian. So both patterns are Poissonian together, which is the case when I modeled this pattern. And at the end, it tend to show some clustering, but we have some effect that we don't want to take into account. So we need to cut the curves around here. So we see that it works. It works fine. And now if we try to cluster the two data sets, so the X and the Y, so the round and the triangles, you will see that for the J function tend to be lower than the Poissonian one, which is still the dashed line here. So it means that we have that the X and the Y are dependent, so they are clustered together. So now it's time to test it in a real world case. So I took the European seismic hazard model of 2020, so the catalog of the ESHN 20. So I took the declustered one. And I tried to compute the function for two regions. So because my previous work was around L'Aquila, so I decided to take exactly the same. So the box here is all the quake that I will that I will see if they are dependent between each other or not. And I decided to take another region that is a bit more homogeneous than this one. Um, so just to see if the function will change or not. So to compute the dependence between two datasets, as I said earlier, we need to have two datasets, and for that I decided to take all the magnitude lower than 4.5, and I will try to compute the dependence between less than 4.5 and other magnitude range. In that case, for L'Aquila, I will see the dependence between less than 4.5 with 4.5 and 5.5, so this magnitude range, and this one, etc., etc. So I can do a lot of magnitude ranges if I want to. And for the second region, I will do exactly the same. So the reference will be less than 4.5, and I will try to see the dependence with higher magnitude range. So what is the result for L'Aquila? In that case, I look at the dependence between less than 4.5, so my reference, and magnitude range of 4.5 to 5.5. And as you can see, so R is in degrees here. So when you increase the degrees, you will tend to be more clustered. So it means that magnitude 5.5 to 5 so 4.5 to 5.5 is clustered around 4.5. This is this is the definition of the G function here. If I do exactly the same for another magnitude range, so I increase by 1 the magnitude, and you see that the slope are way different in that case. So it means that if the slope is different, when we will be able when we want to model the new okay when we want to model the new distribution of point, we can base our simulation based on the slope of the J function. It will be more clear just after, but just remember that the slope can change, and we can also increase again the magnitude, and sometimes you will have some effect due to due to the number of points. If you don't have a lot of points into your area, so here I don't have a lot of 6.5 earthquake greater than 6.5, you will have maybe some problem into your J function. So for the second area, I did the same. We still observe uh, a clustering effect. So 4.5, so 4.5 to 5.5 are clustered around 4.5. And if we increase again the magnitude, since we saw that the distribution are more homogeneous into the space for that region, if we increase a bit the magnitude, the J function tend to be very close to the Poissonian one. So maybe in that case, it is not usable. So now what we want to do is, based on the J function that we have now, we want to create a new catalog. We want to create synthetic catalog instead of having the rupture totally homogeneous into space. So the localization of I don't know, greater than 6.5 are totally homogeneous into space. We want to constrain the generation of the new earthquake into space. And in using this function, we will be able to do that. So I will not enter into detail into the model creation that I did, uh, but just some example in this case. So this is a region of L'Aquila. You have all the magnitude less than 4.5 here, and the catalog, you can see some of the 6.5 around here, greater than 6.5. And when I try to simulate, so I generate a new catalog, a new synthetic catalog. So my 6.5 will be recreated. So the localization will be recreated. So this is a sample of what you can get when you try to see where will be the new 6.5 localization. Okay. And now what we want to see is that we want to see if the model is working well or not, because the goal at the end is to replicate exactly the same J function when we simulate it than the one that we computed using the catalog. It means that if we generate a lot of synthetic realization of the catalog. So if we generate a lot of 6.5 around the 4.5 using the J function, we need to retrieve exactly the same as we did we need to have the same J function that we have for the when we compute it for the catalog, because the catalog is still the reference. We want to model exactly the same as the catalog. So the black curve is the J function for the catalog. Each gray curves are the J function for one synthetic. So here this is one synthetic, but I will generate 500 of them, and then I will compute the mean. And as you can see, the mean is quite well fitting the J function of the real catalog. And obviously we can do the same for a different magnitude range. So I'm still in L'Aquila. So you still have just one simulation for the 5.5 and 6.5, or the 4.5 or 5.5. So okay, so when you try to compute the J function, depending of the magnitude range, it will be the fitting of the mean curves of the mean G function will be good. So the black is still the one from the catalog, and the gray are still the synthetics. But as you can see, depending of the magnitude range that you are looking for, you may or may not. Sometimes you can find something good, a good fitting, and sometimes you will not have a very good fitting. So I'm already working on a new step to improve it, but I don't have time to talk about this now. But maybe in the next presentation of thread, I will do it. But the next step, so I want to test the performance of the new model compared to the current model used for distributed seismicity. So I have some ideas how to test it. So just testing, just creating some synthetics and looking at the mean of the J function with the J function from the catalog is a good way. But there is a lot of new things to do it to do the test. and I need to do all the tests. After the test, if the tests are good or not, I will maybe go on the computing the aleatory variability of the new model and analyzing the differences with the previous model. So the aleatory variability that I computed during my first year of PhD is like a reference, and the goal is to reduce the aleatory variability. And I hope with this model it will be reduced. So let's see if it will happen or not. And we still aim to improve the new model by incorporating additional rules into the rupture distribution. So again, into the next presentation, I will show you how I did and what would be the new things that I want to add. So yeah, thank you.
Okay, thanks a lot, Jarod. Okay, so any questions for him? I'm gonna ask the first one, which is a very generic questions. Have you got any plans for starting to write a paper on what you've done so far, Jarod?
So the first one on the aleatory variability, I already write it, but
Okay,
I just need my supervisor to review it. And this one, I don't think I'm able to make a paper for now. But uh,
so
but
far,
yeah,
yeah.
yeah.
Okay, good. Danielle, you raised your hand.
Me actually. Is the mic on?
All
Yeah.
right, okay.
Can you hear me?
Yeah.
Yeah,
Okay.
sure.
I was just wondering because there's quite a difference between the two different magnitudes that you have tried. Do you know what the reason for that is?
So the main so so when I compute the J function, actually the only difference in that case are the number of earthquake that you have and the localization. So in that case, it depends a lot on the study area that you I mean the study area, because in that case, if I go again to the first one, where it is, okay. Since this one you have some preferential distribution of rupture, in that case you may have some differences in the J function compared to this one, even if you have exactly the same number of earthquake. But there is some function that correct it. I will not again enter into details because it will take a lot of time. But yes, and the other differences again is in the number of point that you have into the study area. So it can have a huge impact. But yeah, I need exactly to test that to see if it perform well or not. But yeah.
Okay. Thank you.
Does that answer, Rachel?
Yes, it does. It does.
Okay. Sorry, I didn't see you. So you're in Munich, I guess. Is that right?
Yes, but Danny is in
Sorry.
Munich.
Yeah. Other questions, anybody? Okay, so maybe we can move on.
Okay. Thank you.
That's okay. Thanks again, Jared. And Julian is next, last
Sure.
but not least.
Let me share the screen.
Yeah,
Okay. Are you watching my screen?
yeah. Yeah, we can. Will you show us some horses or, or pizza was the last
No,
time?
not today. I'm so sorry.
Okay,
Yeah,
all right.
next time, I promise a new one.
Yeah, yeah. You used we kind of used to new analogies with you. Okay, go ahead. Yeah.
Sorry because I create high expectations before. So, okay. Hi everyone. So, as always, so this is a little bit about my update. So mainly for Daniel and Hoda. My project is about assessment of the impact of advanced seismic hazard modeling approaches in earthquake risk. So a little table of content. So it's a little bit about the work already done, the additional work we were doing, and some future work. So a little bit of the work already done. So uh, I already mentioned the topic, so it is quite open topic. So I was trying to search what is exactly the question I need to solve, because it's like how to test whatever you want from the hazard in the risk. So I found that my question is what if? No. So what if we change something in hazard and then we test it in risk, like the Marvel series, the Marvel comic sets. So as the next step, we tested what if we change the side effect approaches in probabilistic risk seismic assessment. So we worked in this. So we presented the results in the EGU last May. We are almost done with the paper. So we are waiting for some feedbacks to submit it, and also with WTW that are part also of my project, we worked into different white papers, one about side effects and the other about ground motion models. And the next what if question we solved it, or we tried to, it was what if we optimize the side grid for PSRA calculation. So this is the pizza one that David was talking about. So in this part, we presented a little bit as a poster in the EGU also. We are working as scientific paper and a GitHub repository to open the codes. That it was the topic I presented to you in my last update. And we hope the paper will be ready this month. So let's see. And also about this, we participated in the Outstanding Student and PhD Candidate presentation contest, and we awarded with the prize. So I'm very proud of this. Sorry, I needed to tell you about this. So after this, so some additional work we did. So the next what if question, it was what if we change the method to estimate the seismic demand for seismic design code? So this is very engineer part. So sorry, because most of you are geologists and geoscientific, but this is very practical and very useful stuff. So about this, we are working a short note paper in Spanish. So the co-advisor are also reviewing this. It's in Spanish because it's we selected as a test as a case study in Colombia, and it is very important because for the new release of the code, there are some discussions. So we decided to do it in Spanish to do it more democratic, let's say, open to the engineer community in Colombia. So a personal, very non-biased recommendation is not biased, despite it's a talk from Helen Crowley, who is the main seat in the GEM Foundation. So this is the journal lecture. She has been performed around the world. So this is the QR. It is this version. It was in the World Conference last year. And it's very interesting because it's the history of the different methodologies to define the seismic demand from the seismic codes, from hazard and risk methodologies. So if you want to see what I'm will talking about here in more deep, you can follow this talk. But about some introduction, so maybe we'll know what is PSHA. So we started with the definition of seismic sources. Then we play a little bit with catalysts, best friends, recurrences, functions. Then we play with a little bit with Rachel's friends, ground motion models. And we finally play with the best friends of Jarrod now in the PhD, the recurrence curves. And this is how we estimate the probabilistic seismic hazard assessment. But the problem here is, okay, we estimate the rates and probabilities to exceed different seismic intensities in terms of PGA, SA, PGV, or whatever you want. But what is the why this is useful? So we need to use the shaking intensities and the probability of exceedance in terms of reduce or mitigate the risk. So it has very example of how to use the result. So for instance, we can estimate the risk, we can see how to mitigate the risk, or we can use the PSHA to estimate, for instance, the seismic demand to design new buildings. So for this, the traditional seismic codes trying to use the very famous response spectra, because it is in terms of acceleration and it depends of the natural period of the oscillator that can be related with the period of the building we are designing. Let me just change here. And we, as engineer, we like the life really easy. So the codes include, okay, you don't need to estimate the response spectra. We provide you a parametric spectra. So depending some factors, we suggest you design a spectra about how to design your building, depending of the hazard and the type of building you need. The problem is that for creating the parametric spectra in a code, so how to do it? No, it is really hard stuff. This is an open question somehow, but it is a necessity to do it in a right way. So there are different methodologies to do it. So the first methodology, of course, is the uniform hazard spectra. So we estimate the different spectral acceleration for a given return period. So if we go, for instance, in PGA and say in 1 second, 2 seconds, and all the ordinates you want, we can estimate using the PSHA all the different intensities for a given return period. So usually the seismic codes define the demand in terms of the probability of exceedance of 2% in 50 years. Or how the engineers say is the demand for a return period of 475 years. So this is beautiful, this is very easy, but it has some questions to solve. For instance, it has some problems. So, for instance, it depends of one return period, but it doesn't depend in all the hazard curve. So, when we evaluate the risk, so in two different sites with the same demand, we can obtain the different risk because the total hazard curve is different. So because of this and other aspects, in 2007, more or less, they introduced the term of risk target ground motion. So this was a new attempt, and they say, okay, let's move from the hazard part to the risk. And let's see, for instance, this is in the first figure here. Can you see my mouse, my cursor? So for instance, let's see this figure here. We have one hazard curve in blue and we have a hazard curve in red. And when we estimate the hazard with a probability of exceedance of 2% in 50 years, we can see that the hazard is almost the same, right? It's almost 1.29 in the blue curve and 1.38 in the other. It's almost the same. But when we estimate the risk, assuming a fragility curves in terms of collapse, the same curve for both sides, we can see that the probability of collapse is very different. So the hazard is almost the same, or it is very similar, but the risk is very different. So they changed it a little bit, the criteria, and they proposed, okay, don't fix the probability of exceedance of the hazard, but let's define a seismic demand would correspond to a fixed probability of exceedance in terms of risk, in this case, in collapse. So in the left panel, you can see the same example I showed previously. And in the right side, we can see now how changing, selecting different points in the two different hazard curves, now the risk is very similar. It's 1% in both curves. There are other details, maybe not enough time to explain this, but the idea is like the criteria is changing from a hazard criteria to a risk criteria, defining a fixed exceedance of collapse. And there is a third methodology, which is named the optimal design. So we have the first one, it was the uniform hazard spectra. The second one was the risk targeted ground motion that depends of the risk of collapse. And the third one is, okay, let's define seismic demand which minimize the total cost of the building in all the lifestyle, the lifetime. So how to do it? Okay, let's assume the initial cost of the building can be defined in terms of the seismic demand. So for instance, if you are designing in terms of PGA, you know, if you need the building to resist a higher value of PGA, so it will be more expensive. And then you have, okay, you have the initial cost, but you have also the future losses expected by earthquake. So if you include the initial cost and then the future losses, the future expected losses in all the life of the building, so you will have the expected total cost of your building. So as a simple example, this is, I took this caption from the paper of Mario Ordaz, which introduced a little bit this methodology. So we have the blue line is the expected initial cost of a building. So if we design the building for a higher capacity, so the cost will increase, right? And we have two different example of buildings. So we have the red one that is in the case we want to design in a low seismicity area, and the green one in a high seismicity area. So if we see the continuous line, it is the expected future losses given earthquakes of the building. So for instance, if we increase the design capacity of the building, so we can expect our future losses to decrease, right? It is a more expensive building, the design capacity is higher, so we expect the future losses by earthquake will decrease. And we will have the dashed line in both cases, in high seismicity area and in low seismicity area. We will have the total cost. So it's the initial cost, the blue one, plus the continued line which correspond to the expected future losses. And as you can see, this function has a minimum value. And this minimum value, which represent more or less the design capacity which correspond to the minimum cost. So as a summary, because I know it was tons of information in few slides, so we have a methodology based in hazard, so the uniform hazard spectra. We have a risk-targeted methodology, which is defined in terms of the probability of collapse. And we have the last one, which the economist loves, which depends of the money, no, not other stats. It depends of the future cost. It doesn't depend of life or collapse, it depends of money. So what we did, so most of you are now expert in hazard in Colombia because have seen this caption many times, but there is a hazard model of Colombia, developed by the Colombia Geological Survey and the GEM Foundation. And we estimate the hazard curves at 1,100 urban centers in the country, assuming road conditions, using SA in 0.2 and 1 seconds that are the most used intensities for design codes. And we estimate the seismic demand using the different parameters. So the first one is the one using the uniform hazard spectra. The second one is the risk targeted ground motion. The third one is a variation, which is the one that is really used in the code. That is 2/3 of the risk targeted ground motion. We calculated also the seismic demand using the optimal coefficient methodologies. And we have this lonely one that is the seismic demand from the current code that was released in 2010. And we compare the metrics. But if we compare the metrics in terms of acceleration, maybe it is nothing. No, it's what means a difference of 0.1 G? I don't really know. So we compare this in terms of the expected probability of collapse using the different methodologies and the total expected cost from the methodology, from the theory behind the different methodologies. What we found is this is the example using 4 different cities in Colombia. We have Cali, Bogota, Barranquilla, and Leticia from high hazard to the lowest hazard. And we can see this caption is in terms of probability of collapse. So the y-axis represent the probability of collapse, and the x-axis represent the seismic demand. We can see the different labels means the different methodologies. And we can see that the different methodologies conducted to really different probability of collapse. So which one to select? Let's see. Because, okay, now we are comparing the probability of collapse, but I told you there is some methodology the economist loves because it is about cost, more or less money. And this is how they change in terms of the total cost. We can see because of the shape of the function, so this is the function, but despite the results in terms of probability of collapse are very different, we can see that the function of normalized cost has like a valley. So even the probability of collapse changed a lot, the normalized cost is not really changing. We are right? The problem here is that, okay, maybe we can reduce the cost, but we are increasing the probability of collapse. Is what I want for the code? Maybe not. So in general conclusions, okay, most of the, as you saw, we got really different results in terms of probability of collapse, but the total cost were very stable, we can say. So we think that maybe the methodologies are not exclusive and we can use it like as different conditions. What I mean, for instance, we know that the seismic codes are changing from the hazard recommendation to the risk recommendation. So let's use, for instance, the risk targeted ground motion, that is a risk-based methodology to define the seismic demand, and the optimal coefficient, which is also risk-based. Now, one in terms of collapse and the other in terms of cost. And we can use both and use the best stuff of each methodology to be complementary. So for instance, we are proposing that, okay, let's calculate both. Let's take as a basis the risk targeted ground motion, But if the seismic demand using the optimal cost is higher than the risk-targeted motion, so let's define the seismic demand using the optimal. Why? Because in this case, we will reduce the risk of collapse and we will save money. So everybody is happy. But in the other case, if the risk-targeted promotion methodology conduct to a higher seismic demand, so we will keep this value. Why? Because in this case, we are also decrease the risk of collapse, and we are increasing the total cost just a little bit. But what is more important, the collapse and maybe the lives or the cost? And the cost is not changing a lot. So we are producing this scheme to include both methodologies and not taking those as exclusive. This is very interesting because the risk-targeted methodologies are the one that are the new trend, let's say like this, to define the seismic codes. And the same result using the optimal coefficient has been also observed in other latitudes, like in Europe. There are some studies. So it seems like it doesn't depend on the hazard model. So we are getting to the same conclusion of other students, other studies. So we believe that our conclusions are general. That doesn't depend of the cases. And about the future work, the last part of the presentation. Now I promise I will keep reading a little bit to publish the papers as soon as possible. I hope I can submit the first two this year. And I will move to Chieti finally next month to know my university. Finally, I will do an internship in my university. So, and this is all for now. Thank you very much.
Thank you very much, Julian. Okay, so time is flying by. So we have time only for a couple of questions, maybe. Anybody? You've done quite a bit, Julian, and congrats for your poster, award. I believe Aurora has won too.
Thank you. Thank you
So,
very much.
we need to put that on a trade report, Bruno.
Yes, I know. We will.
Yeah.
Maybe also in the website and also the others, if there's something to be advised, let me know.
So questions for Julian? So, well, it's not specific to your work really, but it's a community I'm not familiar with. I mean, for example, this paper that you're trying to write, to what journal will you submit it?
The journal, you mean?
Yeah.
For the paper in Spanish?
No. The one that you've been trying to push recently.
Yep. The one of side effects, right?
Yeah.
I already received the feedback of Vitor. We are waiting for the other, but we hope we can submit it to Earthquake Spectra. Let's see, because you know that the times in the spectra sometimes is very long.
All right. No, I'm not familiar with this journal, to say so.
Normally the times are very long, but maybe is the right journal for this kind of papers. It's very specific work because there are not a lot of works relating the difference of different side effect approaches on risk. So maybe this is the right one. Let's see.
Yeah. So you've mentioned a few other, students or PhDs. in one of your slides. I mean, did you actually work with all of them, or were you, you know, playing with the concept on your own in any case?
What you can you repeat the question, please?
Yeah, at some stage you mentioned that you were, you know, playing with, you know, the Gutenberg and, you know, the ground motion models and so on, like, you know, like other people do, like in the trade program. I mean, have you been working actually with, you know?
No, with them. It's
Okay,
just
no,
because
right.
I were trying to link the figure with the work of the
no, I
others
understand
because
that. Okay.
it's more a little bit didactic, but we are not working
Yeah.
for now together. But I will
Yeah.
bother Katere and Jarod very soon.
Yeah, because I mean, one of the aspects of trade at some stage is to interact, you know, between the students. So I was wondering if you actually already did that.
Actually, for my secondment at Kieti, the initial idea was to start working with Katere, but we will work together maybe, but not in presence. So more or less, when I come to Kieti, Katere is already left. So it is good and it is bad. It is good because I will take her apartment, so everything is going well. But it's bad because we are not going to be together. But
yeah.
so let's see.
Right. So there's a trade apartment in Kitty waiting for
More
you.
or less. More or less. Mhm.
Okay, good. I think we need to move on unless there are, you know, specific questions. Anybody?
I have a question, not to
go ahead,
Julian, but a generic question. So we have the training school in September in Portugal, but what about the November workshop? Is that happening? Do we know when that is happening? Because I foresee some schedule conflict, so I'd like to know for planning.
Bruno, do you want to answer this one? Oh, we mentioned that. Oh, yeah.
Sorry, I lost the question. I was answering another. Please, Alexander, can you repeat the question?
Yes, so we now we'll have the Portugal training school in September, but what about the like November-ish workshop? Is that happening? When is that happening? I just yeah, want to plan some things.
Yeah, we didn't discuss it yet. I will let you know as soon as possible about that. I will have a meeting with Vitor and Marco, and I will let you know as soon as possible.
Okay. Do you have an idea when that will be? Because I already just need to schedule some other things for them.
Not yet, but what you can do, and also the other students, let me know when is not possible because you are busy. So we can fix in another period. So if you have something that is planned and really important for your project, don't hesitate to let me know, so we know that we have not fixed in that period.
Okay, thank you.
We are late. Sorry for that.
Okay. All right. So let's move on. So we have a lecture by Alessandro, and he will talk about something that is mostly important in earthquake physics and risk and everything. So you're going to talk about fault interaction and earthquake interactions, if I'm correct. So that's, that makes a case for, why, seismicity is not, as boring as hell, because it is clustered in time and space. And, and we are still, struggling to understand all these interactions. So please go ahead, Alessandro, and I hope we'll learn a lot from your lecture.
Okay. First of all, can you hear me?
Yes.
Perfect. I will just share my screen. Here it is. Let me remove this thing.
That wasn't looking like Germany at all. I mean, you first.
No, that's not Germany. To be honest, that now doesn't look that bad, at least in terms of weather.
All right.
Can you see my cursor here? Maybe I can
Now we can see it.
annotate something. I always okay. Okay, so David already anticipated some of the conclusions or of the talk, of course, but we already knew that. I'm going to talk, about fault and therefore earthquake interactions at different spatial and temporal scales. I hope most probably I'm going to bore some of you with some of the topics because many of you already have the concepts of this, at least the methodologies to study earthquake interactions. But I'm going to talk about different, let's say, expertise that goes from modeling to geology, seismology, and paleoseismology and hazard. A little bit about risk. I'm sorry, but I guess we can connect with hazard. So I will start from the basics. I guess it's always good to, as the Romans say, repetita iuvant, to repeat the basic. So when we talk about fault interaction, first of all, we immediately think about the concept of critical Coulomb failure stress. And that the main hypothesis is that the faults interact by transfer of stress. There is a very nice, let's say, analog model done. If you watch one of Rostein's video trainings, this is the classic that he's gonna show you, where he tries to basically with a simple model explain what is happening during earthquake interaction or fault interaction with basically a simple model with a winch, a spring, and a brick. The spring is gonna be our elastic crust. A very simple model. The contact between a brick and the surface is going to be basically our fault. There is some normal fault, a normal stress acting on the brick, of course, due to the weight of the brick. And there is some friction between the brick and the surface, which is basically related to the roughness, let's call it, of the surface. There is a force balance, of course. The brick will not move until the force on the spring will be equal or larger than the force resisting the motion. So basically what we do, we basically activate the winch and the spring basically loads the surface, our fault, and at a certain point, our brick is gonna move and is gonna create our stick slip, how let's say the experimental geophysics like to call it, and our earthquake. And this is a simple case where we have one single fault, and if you do this multiple times, you will see that our fault rupture with some kind of recurrence time, let's call it. But what happens if we put another brick in there? Let's say we put in series another brick connected to the first brick, the purple one, with another spring. Let's say that the spring has the same characteristic of the previous spring, that basically is the characteristic of our elastic crust. We repeat the experiment, and of course we have our first purple brick moving and creating, let's say, our earthquake. And while the earthquake, let's say, while the brick is moving, what it does is also load the spring connected to the brown brick, therefore loading the other fault, the second fault. And at a certain point, let's say, the other fault will break. How we call this system? So basically, our first purple fault is going to be the source fault, which loads with the earthquake that occurred on the source fault. The second fault is the brown one, which is the receiver fault. And if we want to resume this in a very simple equation, we bring in the concept of critical Coulomb failure stress, and in particular of stress changes, Coulomb failure stress changes, that are basically, you can easily, let's say, calculated by the sum of the shear stress change plus the normal stress change multiplied by a certain friction coefficient. This is, let's say, an alternative way to show that. If you have read paper about earthquake interaction, for sure, the first thing that come to your mind are these, let's say, colorful figures, like you can see upright. You see some blue, and if you're lucky, let's say, you see some blue and red colors. If you're not that lucky and you're colorblind, you will see also some green, which is not, let's say, this is what you see in the, let's say, the first papers that came out about Coulomb failure stress, where, let's say, the zero stress change were not white, but were, let's say, green. And for the, let's say, 10% of men, actually, that are colorblind is not very nice to look at these figures. But anyway, we have our source fault, which is in this case is a strike slip fault, A, and there are some receiver faults surrounding the source fault. The B is located in a red area, so is brought closer to failure by the earthquake that is produced by the source fault, while the C fault is located in the stress shadow, and theoretically that fault is brought further away from failure. What you see here is a simple 2D figure. Usually, what you have as an input for this calculation are information about the source faults, that are, of course, the size, the geometry in general of the source fault, the slip model on the source fault. At the very beginning, the very first models were based on homogeneous slip models, but now we have much more information to add, so we can build heterogeneous slip models based on the slip inversion of geodetic data, for example. And our source fault has the deep strike, a rake, of course, and the receiver faults as well. So every time we see a calculation like that, we have to think that the calculation is on a specific strike, so one number basically for your receiver fault, one specific dip, which is again one number, and one specific rake of the source of the receiver fault, which is again one number, so one kinematic. So every of these, let's say, representation of stress changes represent one single particular condition of strike, dip, and rake. You can do the classic calculation are the so-called coseismic stress changes, which represent the instantaneous elastic stress change due to an earthquake, basically. What you can do as well, using a little bit more complex model, not that complex, but a little bit more, is some time-dependent stress calculation. And we'll see later what it is. Those are mostly due to what we call after-slip, viscoelastic relaxation, or poroelasticity. We'll see later what that means. So the first, let's say, approach used in Coulomb stress interaction, that is basically the party that we'll talk less here, just a couple of slides just to let you know, but probably you know already, is the interaction between the main shock on a fault and the distribution of aftershocks. This is an example from the Darfield earthquake that occurred in 2010, a magnitude 7.1 in New Zealand. You can see the distribution of aftershocks that are the black empty circles with the distribution of stress changes. Usually these calculations are done on so-called optimal oriented faults. The optimal oriented faults depends, the orientation of optimal oriented faults depends on the regional stress orientation and magnitudes, which are taken as, say, homogeneous in the study region. We can see already some kind of limitation of this kind of calculation that takes into consideration the fact that the optimal oriented faults calculated are based on homogeneous stress change, homogeneous regional stress. And we already know that in actively tectonic regions, the regional stress is not really homogeneous, mostly at these large scales. what are the limitations of this kind of approach? Of course, it does not always work perfectly. It works better for off-fault aftershocks, so those aftershocks that are located, let's say, a little bit far away from the source fault. And David knows better for sure, and he has done a lot about this topic. While we see quite good observation in terms of relationship between, let's say, nucleation of aftershocks and increase of seismicity in area of stress increase, there is not so much evidence about the opposite. So we expect an increase in seismicity rate in area characterized by stress increase. Therefore, we also expect a decrease in seismicity rate in area characterized by negative stress changes. This is not often the case, and you can, of course, if you're interested in this topic, you can look at the David paper in 2003 and Felser and Brodsky in 2005. What are the main reasons? First of all, mostly for earthquakes that occur, aftershocks that occur very close to which are the vast majority of aftershocks, very close to the source fault, to the main shock. Our calculation of stress changes rely on slip model. To the right, you can see an example of how many different slip models can be, let's say, generated or has been published by different authors, only about one basically sequence of earthquakes, which were the ridge crest earthquakes. So if we start studying and modeling the relationship between aftershocks and those main shocks using every time different slip models that are 9 slip models, plus the one generated by the author of this paper, so 10, we will see that the results are pretty different. So this is already a quite big limitation. Another limitation is that these models do not take into account the fact that aftershock may trigger other aftershocks. Therefore, it's not that every aftershock is triggered by the main shock, but you can have also aftershock triggered by largest aftershocks that occur after the main shock, let's say. And I was saying, we don't really know the receiver fault mechanism of every aftershock that we study, as we usually do this optimal oriented faults calculation, but we don't know is the faults that are reactivated during aftershock sequences are not always optimal oriented, and we rely again on the regional stress orientation, which are not always homogeneous. If you want to know more about this topic, I suggest you to read this paper from Sharma et al., which already the title says a lot. Is Coulomb stress the best choice for aftershock forecasting? A lot of information about that there. But what I want to talk about more is relationship and interaction among big faults. And so stress changes and earthquake sequences. And I want to start from, again, the first paper that came out. You can see an example of this, what I was talking about with the red, blue, and green color scale. So I'm sorry for that. Not really my fault, but I have to reference these papers. So it's all started more or less as always, in California with these studies. With the work of King et al. In 1994. What they did is basically model the Coulomb stress change due to several earthquakes preceding the 1992 Landers earthquake, the 7.3. You can see the figure to the left. This is a model basically of the Coulomb stress changes due to these 4 earthquakes, 1975, 1979, 1986, and 92. Events in the Eastern California shear zone. They all preceded the famous 92 Landers earthquake, which occurred right here, where you can see the star. And the conclusion of this paper is that all these preceding main shocks created a region of stress increase right where the Landers earthquake enucleated. But this was not the end. basically 3 hours and 26 minutes after the Landers main shock, another earthquake occurred on another fault. You can see here to the right, the Big Bear earthquake in magnitude 6.5. This is, I would say, quite a lot of earthquakes in a very short time. So between 1975 and 1992, we'll see there will be another earthquake in 1999. Considering that we are in a region here where slip rates of faults are not very high, so they are below the millimeter per year, more or less. So it's not the San Andreas fault where we have centimeter per year of slip rates. We have here 1 to 0.5 millimeter per year of slip rates. That means that we expect recurrence times for those faults of thousands of years. So having so many earthquakes occurring in such a short time scale, it's quite uncommon. That's what we call basically a cluster of events in very short time scale and also spatial scale. But if we think about sequence of events or a cascading sequence of events in a, let's call it domino effect, the most famous and the most stunning example is what happened and what probably is still happening on the Northern Anatolian Fault. So this is a plate boundary fault. So we are talking here about very high slip rates on the centimeter per year. What happened is that what you can see in this figure from east to west, it's starting from 1949. There was a sequence of events, those one to the east, but smaller, but the 1939, sorry, the largest one, which migrated from east to west along the Northern Anatolian Fault. The 1931, you can see it here. This is the cumulative bilateral slip. So basically, all this area below the red area is proportional to the magnitude of the event. 1942, 43, 44 here, 51 in the middle, 57, 67. So a very clear domino effect that was, of course, explained by a paper of Stein et al. With Coulomb stress interaction. Very simple. Actually, it's a nice model, but we could expect such a behavior to be explained by stress changes, static stress changes. The interesting thing is that the paper was published in 1997 and highlighted the fact that there is a region, of course, to the very west, which is characterized by high stress increase, in particular the region around Izmit. What happened in 1999 is the famous Izmit earthquake in a magnitude 7.4 that was followed few months later by another 7.1, the Duže earthquake, which this time was not to the west of the Izmit, but let's say the rupture came back to the east. You can see here the Izmit occurred right here. This is the stress changes before the occurrence of the Izmit. This is the stress changes after the Izmit earthquake with the location of the Duže earthquake that occurred 3 months later. So this is the most stunning and the classic example that everybody will talk about in every paper when they want to talk about domino effect in terms of Coulomb stress changes and triggering. If you look in the Google Scholar, if you look for Coulomb stress changes, earthquake interaction, you will find plenty of papers. It will take forever to list all the papers, to list all the sequence of events, which has been studied and modeled and explained with the static stress interaction. Some a little bit more recent events are, as I mentioned before, the Darfield earthquake and the Christchurch earthquake, the 7.1 in September 2010 in New Zealand that was followed by the February 2011 Christchurch earthquake. This is basically the slip model of the first earthquake used to model the Coulomb stress changes on the location of the second earthquake, and you see the basically the increasing Coulomb stress right where the hypocenter of the earthquake is located. And the most recent example are the Turkey and Syria earthquakes, where basically a 7.8 on the East Anatolian Fault was followed by a 7.5 on a, let's say, off fault. Again, not on the East Anatolian Fault, but on a close by fault, which is big enough to produce 7.5. The 7.5 occurred basically 9 hours after the 7.8. One thing that you may notice, if you look at the magnitude of these stress changes, either they are in megapascal or in bar, is that those magnitudes are very small. In this case, we talk about 0.03 megapascal, so 0.3 bars. 0.3 bars. In this case, we talk again 2.5 bars, so similar magnitude more or less. And this is when we compare these values to, for example, stress drop of large earthquake that in average are, let's call it, around 30 bars or 3 megapascal. This is very little compared to those stress drop values. That means that those faults, those earthquakes had been triggered because those faults were already very close to failure and probably at the very end of their seismic cycle. So, I was talking until now about basically co-seismic effects, instantaneous effects, but what about time-dependent transient effects? In general, there are three major groups of time-dependent effects. The first one is the after-sleep. Basically, what happened after a main shock or large earthquake is that the fault continue to move. This time not seismically, and not very fast, like during an earthquake, but slower and aseismically. Doing that, the fault and a seismic slip on that fault transfer additional stress in the surrounding. So we have additional stress, additional to the co-seismic stress changes that has been transferred in time on the same fault, but could happen also on the nearby faults. We have poroelasticity that is a less known effect, I would say. If you will look for papers, you'll definitely find less papers talking about poroelasticity or poroelastic rebound after earthquakes compared to after sleep or viscoelastic relaxation. What happens basically after an earthquake is you have, of course, strain and stress changes in the surrounding rock matrix. And these stress changes and strain deformations create an heterogeneous pore pressure field. So you have areas of, let's say, increased pore pressure and areas of decreased pore pressures. And what happened in time, so this is the time-dependent effect, is that the fluids from areas of increased pore pressure will start moving because of the gradient that has been created towards the areas of decreased pore pressure. And doing that and considering there is a coupling between the fluid flow and the rock matrix, which is called linear poroelasticity, will create stress changes in the rock matrix and time-dependent evolution of these stress changes. Like after sleep, this process can last from days to few months. And at the very end, there is the viscoelastic relaxation, which is the process that lasts longer, so years to centuries even, and is due to the time-dependent relaxation of the viscous lower crust and the upper mantle. While we consider the upper crust elastic, what is below, so the lower crust and the upper mantle, are considered viscous. So right after an earthquake, the instantaneous behavior of our lithosphere is always elastic. However, what happened after is that the lower crust and upper mantle try to regain the previous shape by transferring stress towards the upper crust, so towards the where our main shock occurred, but also towards other faults in the surroundings. Let's go fast towards the after sleep, let's say through the first two. The after sleep, an example, again, I go back to the August Izmit and November Dusha earthquake. There is an interesting paper by Ern et al., 2002, where they actually try to explain why those two earthquakes occur with such a delay, and not why the Dusha earthquake didn't just happen immediately right after the Izmit earthquake. And the conclusion is that the stress changes alone, the static seismic stress changes alone from the Izmit earthquake were not enough to trigger the Dusha earthquake. And their idea, their hypothesis is that the fault, the Izmit fault, continued to move aseismically. You can see here the slip models estimated with inverting GPS data. Aseismic slip 10 days, 20 days, 40 days, and 80 days after the Izmit earthquake. And you can see that up to 0.4 meters of slip were modeled for 80 days after the earthquake, which is not a little amount. And this is the result of their model. Basically, the star here is the location of the subsequent earthquake, the Dusha earthquake. And the top figure shows the coseismic stress changes, yet positive in megapascal. However, in time, so following 20 days, 40 days, and at the end 80 days after the earthquake, the stress changes on the Dusha earthquake hypocenter increased due to this after sleep effect of the Izmit earthquake. So there is a time-dependent increase in stress that follows let's say, the more instantaneous coseismic stress increase. That in this case could explain why the triggering of the second event was delayed by a few months. In terms of, let's say, poroelastic transient of Coulomb stress, so poroelasticity, if you remember in the Coulomb stress change equation, there is this value, which is the friction coefficient, or effective, that's called friction coefficient, which in the, let's say, in the coseismic stress calculation is defined by the normal friction coefficient multiplied by 1 minus b, which is the Skempton coefficient, which is assumed to be a constant value in this case. However, let's call it the original, the real equation of Coulomb's failure stress takes into account pore pressure changes. And pore pressure changes are not instantaneous, but they evolve with time. And this is what basically Tung and Masterlach did, try to understand in central Italy, right after the Amatrice earthquake, so the 6.2, the first of the sequence. A few months later, before the largest one, the 6.5, another earthquake occurred northern to the Amatrice earthquake, which is the Visso earthquake, and was a magnitude 5.9. They use a magnitude 6.1, but it doesn't matter. What they did is they modeled this poroelasticity and this time-dependent evolution of pore pressure and time-dependent evolution of stress changes. In the first figure here to the left, you can see the Coulomb stress change, so the coseismic Coulomb stress change calculated on the epicenter of the hypocenter, sorry, of the Visso earthquake, which was indeed positive. Then to the right, what they did is to calculate the pore pressure changes due to the Amatrice earthquake. And they noticed that in the location of the Visso earthquake, there was a decrease in pore pressure, while in the surroundings, there was an increase in pore pressure. So according to their models, according to the theory of linear poroelasticity, what will happen in time is that let's say the fluids will travel in times from the region of increased pore pressure, so the red regions, towards the regions of decreased pore pressure, so the blue regions. And this will create a time-dependent stress increase on the location of the Viso earthquake. You can see this time-dependent evolution in this dark, it's a black curve here. So this is the days after the Amatrice earthquake, and you can see the evolution of the Coulomb failure stress going from values here of, let's say, 20 more or less kilopascal. So this value is basically the coseismic Coulomb stress changes, and then it increases with time up to 8 days after the earthquake. So when the Viso earthquake occur, basically the Coulomb stress changes increase by, let's say, 4 times compared to the coseismic stress changes. So again, this is also an interesting approach, trying to explain the delay between the first event and the second event, and why the Viso earthquake, the reason why the Viso earthquake didn't occur right after the Amatrice event. Okay, now I'm going to talk about my favorite topic in this case, which is the topic where I did most of my works in terms of Coulomb stress changes, which is the post-seismic viscoelastic relaxation. I want to show you this simple example where we have, again, a strike slip fault producing a magnitude 7.1 earthquake. And this is the coseismic effect. I want you to focus on the green dot, if you can see it, is right here. Sorry again for the colors. And I'm gonna now scroll towards different times. So the next slide is gonna be 1 year after the earthquake. So not so much changed in terms of stress changes. Then 5 years, 10 years, you see how everything changed more or less. 50 years, 100 years, 200 years. And you see that certain evolution of stress changes, both in this case, in spatial, but also in terms of magnitudes. This particular model was made assuming that the lower crust has a viscosity of 10 to the 20, while the upper mantle has a viscosity of 10 to the 19. So look at where the point is, and the next figure is going to show you the evolution in terms of Coulomb stress change in time of that particular point. Different curves represent different models where we basically tested different combination of lower crust and upper mantle viscosities. The main message I want you to take from this plot is that from an initial coseismic stress, which was around 3 bar, we reach in time a value which is double, basically, the initial coseismic stress. We go up to 6.5, 6.3 bars. How quickly we reach that value strongly depend on our models, on our viscosity values. Of course, higher viscosity means that the lower crust or upper mantle takes longer to relax, while lower viscosities means that, like in the, let's see, this reddish curve, the model one, the lower crust and upper mantle takes very fast to relax. So it redistributes stresses quite quickly. Some examples of try to understand the relationship between different earthquakes are shown again for California, for the Hector Mine 1999 earthquake. This is an event that followed the Landers earthquake, the 1992 earthquake. You can see the fault responsible for the Landers earthquake right here, and the Hector Mine occurred right here. This is in yellow and black, the fault responsible for the Hector Mine event. What you can see from the simple model is that already with coseismic stress changes, you could theoretically explain the interaction between those two events. But the authors of this paper, Fried and Lin, found that, again, using different slip models for the Landers earthquake resulted in different results. So some models were showing that actually the Hector mine hypocenter was located in area of stress decrease, other model of stress increase. And their conclusion, the first conclusion, was that coseismic stress changes alone could not explain the delay time between those two events. So what they tried to do is a modeling viscoelastic relaxation, so a more time-dependent approach. This is let's say, a view in 3D. What you can see here, more or less, sorry if the figure is a little bit blurry, the white line is the Landers earthquake, and the black star is the location of the Hector mine. In terms of coseismic stress changes, it's located in an area of, let's say, threshold between negative and positive. However, if we take into account 7 years of viscoelastic relaxation, in this case coseismic plus postseismic, in this case postseismics only, up and down are two different kind of models. So the model up is where the lower crust has with a viscous lower crust. The model down is with the viscous upper mantle. In any case, both models show that postseismic stress changes increase and brought the fault responsible for the Hector mine earthquake closer to failure. And so basically, this is a plot showing the results in terms of stress changes exactly at the location at the hypocenter of Hector mine. Basically, the idea was that viscoelastic relaxation, 7 years of viscoelastic relaxation were responsible for the, let's say, triggering of the Hector mine earthquake. Other examples come from Mongolia. I will scroll pretty fast towards this. There were four main earthquakes in Mongolia between 1905 and 1957. Those events were very far from each other. And for example, this is the event in 1931 with Coulomb stress calculation on the Gobi Altai fault, that is the fault responsible for the 1957. Considering the big distance between these faults, coseismic stress changes were not enough to explain the possible interaction among these faults. And Sherry et al. Again tried another approach based on viscoelastic relaxation. And what they saw is that considering viscoelastic relaxation, indeed, they could explain these long distance, but also long time interaction among these faults. There is more than 20 years between those two earthquakes, and there is indeed more than 400 kilometers distance among these two earthquakes, among these faults that generated those two earthquakes. So another work that we did, that I did during my PhD, is to focus in a basin and range, and considering historical earthquakes, but also paleoseismological earthquakes. So here we are in the Western United States, so an event that occurred 500 years ago is already a paleoseismological earthquake, because of course, if we compare the observation of earthquakes of the Western United States with regions like Italy or Greece or Europe in general, nobody was living in Western United States 500 years ago. At least there were people living there, but nobody was recording earthquakes 500 years ago. So we don't have so much knowledge about events that occurred there, let's say, before 200 years ago. So that's why we called everything that happened before a paleoseismological earthquake. I focused on several events. In this case, those three events are all paleoseismological events. And we noticed that there is some certain correlation among these events that occur in a cascade between 1375 and 1605. What you could say is that, okay, this is paleoseismological event. How you know exactly the date of these events? We don't. So this is basically the average of the range of the occurrence dates calculated with paleoseismological studies. So this number is just an average, not the exact date. We found also similar correlations among historical earthquakes in a little bit to the east. In this region, where several earthquakes occur in 1954. And what we found is that basically the previous event created a region of stress increase in this particular spot here. And in 1954, a sequence of 5, I think, earthquakes of magnitude between 6.9 and 7.5 occur in this region, basically on a time range of 1 year or less. So our conclusion is that that particular region, that particular area was affected by several historical and paleoseismological earthquakes that brought closer to failure all the faults located in this area. Continuing in the same region, a little bit southern, after the Ridgecrest earthquakes, we did a little bit more modeling, taking into account some earthquakes that occur a little bit south. And we calculated that basically the Ridgecrest earthquakes occurred in a region that was characterized by coseismic and post-seismic positive Coulomb stress changes due to historical and paleoseismological earthquakes that occurred before. So again, the occurrence of the Ridgecrest earthquakes was not random, but possibly related to the occurrence of previous events. And this is basically a more fancy way to show Coulomb stress changes distributed on the 3D geometry of the fault. You can see where the 6.4 event and the 7.1 were located, and you can see that basically all the faults and smaller faults that were involved during the Ridgecrest earthquakes were characterized by positive Coulomb stress changes. An interesting thing that how we can use these results is also in the dynamic models. This is what Tofik did in his paper in 2023, where basically used our results of stress accumulation on the Ridgecrest faults to as an input or one of the inputs to model to do dynamic models of the two events. You can see here their preferred models. So basically the model that fit better their observation. This is the foreshock event. So the first event, the 6.4, sorry, with slip distribution on two faults, F2 and F1. And this is the second largest event with involving the largest fault, F3, and also partially the F2 and F4. If we don't take into account the long-term stress changes due to previous earthquake, our dynamic models or their dynamic model look a little bit different. Mostly the foreshock, so the first event, which basically only without long-term Coulomb stress changes only seem to rupture one small fault F1 and not propagate to the F2. You can see here the time evolution of the moment release, also very different between the green one, which is the model without long-term Coulomb failure stress, and the black one, which is the preferred model, basically. There is some differences also in the second event, the main shock, but not as strong as in the foreshock. I want to move now to Italy, again with the same topic, since most of you or some of you work with earthquakes in central Italy. We tried the same approach with normal faults in Italy, try to understand how viscoelastic relaxation on slightly smaller earthquakes can in time change stresses in the surroundings. So those are three simple models of a magnitude 6, a 6.5, and a 7 normal faults. And the colorful lines that you see are isolines in time that represents the 0.2 bar isoline of stress changes. 0.2 is, let's say, a threshold that is usually used to explain earthquake triggering. What you can see very simply is that for a magnitude 6, the isolines don't travel, let's say, in space so much. So the effect of viscoelastic relaxation is not that strong in terms of areal distribution. It starts to be important, let's say significant, with a magnitude 6.5. You can see that the difference between the coseismic and the 200, 250 years is definitely significant for larger earthquakes, as expected, for a magnitude 7. This is again a similar plot as before. For every line represent a different magnitude of earthquake, and here on the y-axis is the distance of the isoline from the fault tip. So how much this triggering front travel in time due to viscoelastic relaxation. You can see that the magnitude 6 basically it doesn't travel so much. It doesn't reach longer distances. It increased by 10 kilometers, let's say with a magnitude 6.5, and by over 30 kilometers if we consider a magnitude 7. This is more or less what I just said. So we use these characteristics to look at earthquake sequences in the historical catalog in Italy and try to understand what clusters of events may be better explained with coseismic stress changes, instantaneous or static stress changes, and which clusters of events may be better explained with the viscoelastic relaxation, so a more time-dependent effect. This is a busy plot. I'm sorry for that, but on the y-axis, you see the occurrence here of each earthquake, and on the x-axis, the distance from north to south. So all the earthquakes here and in the northern part of the Apennines, here in the southern part of the Apennines. So we wanted to define the short-term triggering when earthquakes are at 10 to 20 kilometer distance from each other and less than 10 years different in time from each other. Everything else, distance, larger time scales, and distances between events that are related to viscoelastic relaxations, examples I showed before, are going to be considered long-term clusters. So we found three basically short-term clusters that we can explain just with the coseismic and instantaneous stress triggering. You can see here the most recent one, the 2016 events. This is the Norcia and the Amatrice and the Norcia earthquake. And we can see other several 5 clusters that are more long-term. Events that are probably associated, faults that probably interact, but in more time dependent and with effect strongly affected by viscoelastic relaxation. You can see that 2016 is also part of a long-term cluster, which started in 1915 with the Fucino earthquake. This is something I will go very fast because I think also Bruno went through this during his presentation. So we just wanted to do some Coulomb stress calculation for this particular cluster, where basically we have more information about, so we are able to do some modeling. We started with the Fucino earthquake that increased coseismically by 0.28 bar the stress on the L'Aquila earthquake in 2009. The post-seismic effect was adding additional stress changes, which reached in the end at 0.65 bar. All these events, including the L'Aquila and the Colfiorito, created a region of positive stress accumulation exactly where the Amatrice Norcia sequence started. And then Of course, the figure to the left shows you just the coseismic effect, and the figure to the right shows you the coseismic plus the post-seismic effect. We're still talking about very, as you notice, and most of this figure, most of the calculation, we are talking about very small amount of stress changes on the scale of 0.2, 0.3 bar, so below 1 bar. So let's say that those faults involved in these sequences were, again, very close to failure already. But what about applying this effect to seismic hazard? How we can translate this thing in seismic hazard? We did a small exercise here, following again the Ridgecrest earthquake, and we noticed that we calculated basically that after the Ridgecrest earthquakes, there was strong increase in Coulomb stress on the Garlock fault, which is this huge left lateral fault located in California. The Garlock fault has a very nice paleoseismological data set. And according to paleoseismological data in two main trench sites, here and here, the most recent events in both paleoseismological sites can be dated around 1500. And the nice thing is that this 1500 earthquake was dated in both the central and western section. That means that they're probably the same event, and considering how big is the fault, that this event probably ruptured the entire central and western section in a huge earthquake. So this is the results a little bit, again, on a more fancy view in 3D. So the stress accumulation on the Garlock fault due to several preceding earthquakes, including the 2019 Ridgecrest earthquake that created this big, let's say, large stress increase, about maximum of 10 bar. So how we include these stress changes in a probabilistic seismic hazard? First of all, we have to understand the recurrence times and the coefficient of variation of this recurrence time of the fault we are looking at, in this case, the central Garlock. Those are all the basically the time ranges of paleo events that has been basically located on the Garlock fault and from paleoseismological studies. What you notice if you look at the numbers, there is a big time step between the last 4 events, and the first 2. So this can already say something about the behavior in terms of slip rates of this fault. So there are 2 main ways of including Coulomb stress calculations in probabilistic seismic hazard, so fault-based probabilistic seismic hazard. The first one is to modify the elapsed time since the last earthquake with this equation again. So the initial elapsed time to which we add the ratio between the Coulomb stress calculation on that fault and the tectonic loading, which calculated here with modeling again. The second method is through a modified recurrence time. In this case, we subtract to the recurrence time of the fault the same value, so basically the ratio between the Coulomb stress and the tectonic loading, which is basically the clock advance or delay, basically. This results in different results. So this is for the seismic hazard expert. Those are BPT curves, so Brownian passage time, which is one of the way to basically show probability of occurrence, time-dependent probability of occurrence of earthquakes on specific faults. On the x-axis, you have the elapsed time since the last earthquake on that specific fault. That's why it's time-dependent. And on the y-axis, you have the probability of occurrence in 30 years. The curves are 2 because one is calculated, the black one with the original recurrence time and TM original, and the red one is calculated with a modified recurrence time, so the other way of including Coulomb stress in the seismic hazard. The black dot represents the probability when we do not consider stress changes. The blue dot represents the probability when we do consider stress changes, but with a model where we modify the elapsed time. You can clearly see that the blue dots follows the same curve of the black dot because we just push the fault in terms of clock advance along the same curve, basically. We need to build a new curve because for the other method, the modify recurrence time, because of course different recurrence time means different shape of the curve. So the red dot represents the probability of occurrence of an earthquake, basically including the stress changes with the modified recurrence time. For this particular example, let's see the difference between the red dot and the black dot, which are basically the two methodology, and also the black, so blue, black, and red is not that high. This is because we take into account when we calculate our recurrence time all the events in the paleoseismological dataset, which leads to a recurrence time of 1,322 years and a very high coefficient of variation of almost 1. But if we think that maybe this fault it's still in a cluster, so it's still having a very high slip rate, so we only consider the most recent 4 events, our recurrence time changed by a lot. So from the previous 1,300 years to this model where the recurrence time is actually 481 years with a coefficient of variation way lower, half the previous one. We notice that as a result, also the probability changed by a lot, goes from around 10% for including Coulomb stress changes with elapsed time, modified elapsed time, up to almost 15% when we modify the recurrence time. So the methodology that we use here also plays quite a big role. So I want to go fast now because I'm talking for almost an hour towards a different time scale. So far I've been talking about coseismic and instantaneous stress changes among earthquakes, among faults that are relatively close to each other, so a few kilometers, and also close in time, of course. I've been talking about viscoelastic relaxation, where basically, or after sleep, but mostly viscoelastic relaxation, where our temporal and spatial scales increase. So our spatial scale go to several kilometers, even 100 kilometers of distance between faults, and the temporal scales goes to tens or even hundreds of years. Now I want to go to even larger temporal and spatial scales, mostly larger temporal scales. So I'm going to talk slowly about earthquake triggering, clustering, and anti-clustering. We'll see what it is over several earthquake cycles. I have to go back to the previous calculations to show you basically this series of events, as I say, that occurred in the Eastern California shear zone around the Landers earthquake and the Hector mine earthquake, very short in time, so within 50 to 40 years. If we look at the same area, at the same faults, but we only look at the paleoseismological earthquakes along these faults, something interesting appears. So this is a nice work that I really strongly suggest to read from Scholz et al. 2010. It shows from previously published data several faults in the Eastern California shear zone. We are again in California, San Andreas fault here. This is San Jacinto fault. So the Pisgah and the Camp Rock faults, sorry, were the faults responsible for the 1992 Landers and 1999 Hector mine earthquakes. If we look at the faults around and we look at the large earthquake history, we can see that some faults, like again the blue faults, the Pisgah and Camp Rock, seem to have events that occur at the same time, more or less, considering also the uncertainties on time range of paleoseismological dating. So first of all, the historical event here with the cross, and then two other events between 4,000 and 6,000 years, both on both faults, and other two events that are common, that basically happened probably not at the same time, but overlapped between 8 and 10 kilo years. The characteristic of these faults that they seem to have similar slip rates. But if we look at other faults around, they don't follow the same, let's say, clustering of earthquake. The Landwood and the Ellendale, they have their own clustering, let's say, producing earthquakes together, at least in two occasions. The Calico Fault seems to follow its own way. And then the Ludlow Fault, which is another parallel strike slip parallel fault. We don't know so much about that. So the idea in the paper and the idea of Scholz is that we have this clustering of faults, clustering of earthquakes occurring quite simultaneously on different faults, because these faults have similar slip rates. You notice that the green ones have similar slip rates, the blue ones have similar slip rates, and the outer here, of course, use the same colors for faults that have the same slip rates and seem to cluster together. Let's call it like that. So this triggering, let's not call it triggering, this clustering, this behaving and producing earthquake at the same time seems to go behind the tens to hundreds years time scale, but seems also to affect several earthquake cycles. I was talking about the Garlock Fault, and similar thing happened to the Garlock Fault, but this clustering happens within the same fault. If you remember before, the paleoseismological dating and the events on the Garlock Fault were kind of heterogeneously distributed in time. There was several events occurring in a very recent time, which means if we consider these events and we calculate the slip rate only based on this event, we will have pretty high slip rate. And then two events occurred between 4 and 6 and 6 and 8,000 years ago. So if we only consider those two events and we calculate slip rates only on two events, then we have completely different and lower slip rates. Even if we consider all the events available in paleoseismological dating, the slip rate will be possibly underestimating what we have only when we calculate slip rate from the most recent event. So the main question is, when we do seismic hazard calculation, where basically the slip rate of faults is a very, very important input, which slip rate we use, the very long term, the short term, or an average? This is an open question, and this is, I think, one of the main questions that we try to answer when we talk about several earthquake cycles and the slip rates, the seismic hazard.
Alessandro, sorry, I'm worried because there's only 4 minutes left and I cannot change that. I cannot increase the duration of the meeting.
Okay. Okay, I will go very fast. I'm basically done. It's okay.
All right.
So going faster, basically, this relationship among faults in Eastern California Shield Zone and San Andreas was also observed for other faults, in this case, the Mojave section of San Andreas and the Garlock Fault again. In New Zealand, similar characteristics, but several faults having cluster of earthquakes, other faults having anti-cluster, so having time when not so many earthquakes were occurring. There was some kind of physical way of explaining, mostly considering weaker and stronger fault and deeper roots of shear zones of these faults. There is some work also in the Apennines, which I suggest you to read. Maybe I can pass you the presentation and some of the references done by a group of Benedetti et al. And Roberts and Mildon, which talk about why these cluster and anti-clusters occur over time and what is the relationship among faults in area of distributed seismicity and deformation, why this actually happen and how we can model. So some take-home messages. We've seen that basically interaction among earthquakes happen at different temporal scales, but happen in terms of clusters, so earthquakes interacting and a lot of earthquakes happening in very short time, but also not so many earthquakes happening in even longer time. So we call this, let's say, very strong subsequent events, occurrence of subsequent event clusters, but we call these times when not many earthquakes occur anti-cluster. So, and these have a big effect. They affect very strongly the potential slip rates that we use on fault. So for who works in seismic hazard, how we can include this observation in time-dependent PSAJ, and it's physics-based modeling the answer, or we need something else. That's all. I had some few slides about dynamic triggering, but I think the most important part is done.
Yeah.
Thank you.
Thanks a lot, Alessandro. You covered a lot already. Yeah, even the dynamic triggering is matters as well.
Yeah, it's. I think it's a topic that needs some time to explain as well.
Yeah. So unfortunately, there's not even 1 minute left. So I don't know if there is a quick question, we can go ahead with this question. Anybody? That would need to be very, extremely short. Or we can, if you want to contact, Alessandro directly, that would be good.
Yeah.
Well, his address is in the mailing, list that you'll get. Yeah, I mean, there's only 20 seconds left. So I'm sorry, I cannot change this, and I tried to fight, but
I thought there was like the talk was 1 hour and then additional
yeah,
time.
but it was we took some time before, and I would be more strict about it. But then it's good to have this chance speaking. So it's going to stop in 3 seconds. Thanks a lot, Alessandro. Sorry about that.
Let me know about questions. Bye.
Bye. Oh, actually, it's still going on.
Okay.
All right.
Awesome.
No, we don't need to worry. So we're going to go quick in any case because it's kind of late.
Yes.
So if you have any questions, I have a couple, but maybe students can go ahead. Yeah, Alexander, you raised your hand. Go ahead.
Yes. It's you showed both that the Coulomb stress change is often pretty small, but also that clustering and so on seems to be quite common. So the question is it only a minor perturbation to like the stress evolution that is enough to lead to that clustering, or is it that cumulatively over multiple events happening around a fault, it does add up to be quite a big impact on the stress evolution?
Yeah, thanks. That's a very good question. So one thing of Coulomb stress change, what I found interesting doing this thing is mostly focusing on regions where outside plate boundaries, right? When we have plate boundaries, we have this huge San Andreas fault, we have a super fast fault, and we theoretically know that an earthquake is going to happen on that fault, and the earthquake is going to be big. What is challenging is try to understand what is happening in this, I call it distributed deformation region. So like the Basin Range, like central Italy, like basically everywhere in Europe, where you have a lot of faults close by with low slip rates and possibly interacting because they are so close by to each other that an earthquake on one can change the stresses, either be positive or negative on not only one fault close by, but multiple faults around. So the idea is that there are so many faults that, like for aftershocks, for example, that there is always at some point some fault, or probably a fault that is closer to failure, right? So this right view of seeing earthquake cycle being always earthquakes occurring on a fault at the same time after 1,000 years, very simple recurrence time. This is all gone when we talk about distributed faulting, because every fault affects one or multiple faults, so completely changing the earthquake cycle on one and more faults. So the idea is that even small, because the slip rates are so low, even small stress changes can create this clock advance, let's call it, which is quite big, because if we think about the fault with 0.5 millimeter per year, and we think about that fault may be large enough to produce a magnitude 7, which is like 3 meter slip, 4 meter slip. It needs a lot of years, many years to accumulate 3 or 4 meter slip. That means that even one bar of stress changes can advance the clock by several tens or even hundreds of years. So I think, sorry for the long answer, that the fact that there are so many faults create the situation where more or less there is always a structure that is more or less ready to go, let's say. But again, this triggering is not always happening. So even when we have magnitude 7 or 6, doesn't mean that there is always a following event that is with a similar magnitude or even larger. Actually, I was thinking about doing a very simple statistical observation of worldwide catalogs and see how many times actually this happened in I don't know, in the last 20 or 30 years. It will be interesting to see how many times this happened in the past.
Okay, great. Thank you.
Sorry, I hope I answered.
No, you did. It was really useful.
Aurora, go ahead, please. You're muted.
Yeah, I
Aurora.
think my question was related to what you just said, which is that we actually don't know which structure is ready to go, and so there could be structures that are very stable, and so even large stress changes are not enough to trigger seismicity. And on the other side, there might be structures that are ready to go, so very small stress changes are enough to trigger seismicity. So my question is, are all these colorful maps and physics-based models really useful especially when we want to integrate all this into hazard models? Like, is it really the right tool to handle our ignorance regarding the stress state of faults?
That's a good question, because I had to admit it's a question that I've been asking myself as well. And we are trying to find out, because for seismic hazard, I think, as Bruno always says, we are quantifying the uncertainties. We are never quantifying the hazard in general. So including Coulomb stress means that we are going to include another uncertainty, right? So the question will be, is this uncertainty with the Coulomb stress really smaller or bigger than the other inputted within seismic hazard? So it makes sense to include it. Does it play a role in the end, yes or no? This is something that we are trying. We have to definitely do better in terms of quantifying and relates these stress changes with seismic hazard. From a point of view of basic science, let's call it like this, it's always interesting to observe these interactions and to explain with the physics-based approaches, let's say simple physics-based approach, this interaction. When we want to go from basic science to applied science, which is basically going from these models to PSAJ, the thing always becomes a little bit more difficult. So this is something that we also have to figure it out, how important it is, and if we really make sense to include it, or we just have to consider just a fault not interacting or completely random behaving. The thing is that for sure we know that faults are not random and they cluster. They cluster themselves. That means that you see, like here in the Garlock fault, that you have period of times where you have several earthquakes occur in very short time, and period of times where very little amount of earthquakes occur. So why this is the case? And we also see that they cluster among each other. So they talk to each other, let's say. So in this specific case, it will be interesting because the Garlock fault is super interesting because for example, what I was saying is that what sleep rate we consider when in seismic hazard for the Garlock fault. The long term, the one associated with the most recent events, we see that if we choose one option or another, the seismic hazard changes a lot. And what we see actually interestingly in the geodetic data is even if we have this strong clustering in the most recent time, the Garlock fault may be right now on so-called anti-cluster period, so a period where it's more silent. This is because of geodetic observations or GPS data have shown that, let's say, the sleep rates, geodetic sleep rates are very low. So the fault is not really accumulating so much stress. So there are a lot of questions to be answered, and I think using this multidisciplinary approach, so modeling, paleoseismology, and geodesy can help a lot. It's difficult in low deformation areas because mostly for paleoseismology, we don't have this resolution of, we cannot go back in time so much. Because if we have an earthquake every 2,000 years, then for paleoseismology, it's very hard to recognize more than 2 or 3 or 4 earthquakes maximum. Yep.
Thank you.
Yeah, I remember that at the very beginning of forecast experiments. So basically trying to forecast seismicity over years in a given region. There were physical models based on Coulomb and rated state, and they all behave quite badly because there's so many uncertainties that we cannot control. So it's quite frustrating because I mean the physics is right, we know, but we cannot use it in a practical sense.
Yeah, I heard that mostly for aftershocks distribution is just the fastest way and maybe the best way to do is to define a distance from the hypocenter of possible triggering and just draw a red circle around, or and depending on the fault, maybe an elongated shape where everything is red and we can expect aftershocks everywhere. Yeah. This is not very, let's say, basic science approach. Is more like
for near fault aftershocks, but even for far field aftershocks.
Yeah.
So it's again, you need to know the pre-stress, and you need to know the faults that there are, and it's not that easy at all.
Yeah.
I don't know if there are any questions left because it's kind of late already. So okay. So maybe we can call it today and thank Alessandro again for a very, stimulating presentation.
Thank you for the opportunity.
Thanks a lot. We'll meet again next week with Mathilde about simulating ruptures, I think, and so it's going to be quite different. But and that will be it for this year. Okay, thanks a lot, everybody.
Bye-bye.
Thank you.
Thank you.
Ciao.
Bye-bye. Thank you, Alessandro.
Thank you.
Ciao.